but this is the solution. I'll just help you to give you the solution. This is the solution. Another example. Find the locus of the following. We want to find the locus of the following complex numbers. The first one says at z minus z1, z minus z1. We normally know that z minus z1 is z is s plus iy. Definitely z1 will be s1 plus iy1. It's just a notation. Now we are looking for this. Arc z minus z1 is equal to pi over 3. The question is, what is z minus z1? Let us first find it. Z minus z1. Our z is x plus iy. The minus z1, that is minus this, it will be minus s1 minus iy1. So we take the real part, that is s minus s1, and the imaginary part, I is common. Let's factorize. So this will be y minus y1. So this is our z minus z1. Therefore, our arg z minus z1 equal to pi over 3 will become this. What is the meaning of argument? Argument simply means theta. Now this thing means theta. And what is theta? This sign means arc tan y over x. But we are not dealing with y now. What we have here is, this is representing our y. This is y minus y1. Y over s, that is imaginary over real, over s minus x1 is equal to pi over 3. From that place, if you transfer this arctan to the other side, we have y minus y1 over s minus s1 is equal to tan pi over 3. The question is, what is tan pi over 3? In degrees, pi represents 180. So because pi is in radian, in degrees it represents 180. So that means pi over 3 will be 180 over 3. And 180 over 3 will give me 60. So in that case, we are dealing with tan 60. And tan 60 will give me square root of 3. So we have found the locus. So our answer is, you see, the locus. This thing looks like something. So it's a straight line. So the locus is a straight line. It's a straight line passing through point s1 comma y1 and as gradient root 3. Why is it that? If you remember, formula for finding equation of a straight line is always given like this: y minus y1 over s minus s1 is equal to m. M is the gradient. So this thing is a straight line. So the locus of this complex number is a straight line. If you consider the second one, which says absolute value of z minus z1 is equal to 2. Absolute value of z minus z1 equal to 2. Remember, this is our z minus z1 here. This is our z minus z1 in this place. What's the meaning of absolute value? Absolute value will now be square root of real part square plus imaginary part square. So this is it will be square root of real part. The real part is s minus s1 square. Remember, absolute value simply means s square plus square root of s square plus y square. But we are not dealing with s there. We are dealing with this. So this is the absolute value of, this represents absolute value of this. Then there's equal to 2 there. If you transfer the square root to the other side, we have s minus s1 square plus y minus y1 square equal to 4. So in this case, this is an equation of a circle. It's an equation of a circle. So we can now say that, therefore, the locus is a circle centered. The center of the circle is centered at s1 comma y1, and the radius is 2 units, because equation of a circle is written in this format. Equation of a circle that is having center at a comma b and radius r is written in this format. You will now see that it is the same thing. 4 is 2 square. This is representing a, this is representing b. So the locus is a circle. So you can practice these two. So you need to find the locus of arg z minus z1 is equal to arg z minus z2. So practice that. Special form of complex number is our next topic there. You remember complex number is written in this format: z equal to cos theta plus I sin theta. So in this case, this cos theta itself, this one, it simply means exponential I theta. That is simply, if they say that exponential I theta is the same thing as cos theta plus I sin theta. Even if you say that exponential, if there is minus there, exponential minus I theta will be equal to cos theta minus I sin theta. So in that case, complex number can now be written as r. Since this one is exponential I theta, it is being proved. So we can say that r is equal to z is equal to r exponential I theta. This theta is in radian. It has to be in radian form. It must not be in degree form. For instance, let's say we want to express z is equal to 1 plus I in exponential form. So we have treated this one before. What we got was, okay, we got our r to be square root of 2 and our theta to be 45 degrees in our previous examples. But because it's an exponential form, we will not leave theta in 45 degrees. Remember, I said the other time that pi simply means 180. So we should know that 45 is just pi, is just 90 divided by 2, which is pi, is just 90 divided by 2. So that will just be pi over 4. That is 180 divided by 4 will be 45 degrees. So in that case, our theta is 45 pi over 4. Pi over 4 is 180 divided by 4. So in that case, our answer is r. Our r is root 2 exponential I theta, exponential I pi over 4. So that is what they mean by exponential form of complex numbers. For more about that exponential, we can also write exponential in terms of sign. Anytime we see sign simply means exponential I theta plus minus exponential minus I theta divided by 2I. Cos simply means exponential I theta plus exponential minus I theta divided by 2. So it's very, very necessary. Let's take example on this. Example. So we prove that sine cube theta is equal to 3 over 4 sine theta minus 1 over 4 sine 3 theta. This is trigonometric proof, but we can apply complex number in proving it as well. So we need to apply this. So we just need to know that sine theta is this. So in that case, sine n theta, whatever n will be, you only need to put n there. This is n theta minus n theta over 2I. Likewise, cos 2. I only need any number that is there. Let's say 4 is there. You only need to put 4 beside the theta. That's all. It doesn't affect anything. It only affects the theta. Now, let's use the idea to prove this. Sine 3 theta, sine cube theta. Let's start with this one. Sine theta is this: exponential I theta minus exponential minus I theta divided by 2I. So there's cube. This is sine. There's cube on it. Sine cube theta. So this is just 1 over 2I cube into exponential I theta minus exponential minus I theta raised to power 3. Now, this will just be 1 over 8I cube. Now, we are left with expanding this. So we need to apply, this is binomial expansion. This is 3 minus 3 exponential I theta 2 exponential minus I theta 1. If you can still remember, plus 3. If you use a Pascal triangle, this is 1 exponential minus I theta 2. And finally, it will be minus exponential minus I theta 3. There's power of 3 here. Don't forget, we have treated I cube. I cube is same thing as minus I. Now, if you expand this, exponential I theta times raised to power 3 is just I 3 theta minus, this is 3 exponential, this one too will be I 2 theta exponential minus I theta. This one will give me 3 exponential I theta. There's 2 here. This will just be dot exponential minus I 2 theta. Then finally we have minus exponential minus I. The 3, we multiply the theta. That will be I 3 theta. So we are going to have minus 1 over 8I into exponential I 3 theta. This should give me exponential I theta, because if you are applying this, you only need to subtract the powers. 2I 2 theta minus I theta will just be I theta. That is 2 theta minus theta is theta. But this one too will be exponential minus I theta. This is because because theta minus 2 theta will give me minus theta. Exponential I 3 theta. Now let's bring the ones that are common together. These two, you observe that they are common. So I can write it as exponential I 3 theta minus exponential minus I 3 theta. This one too, 3 is common. Let's factorize. If I factorize 3 out, I will have exponential I theta minus exponential minus I theta. Because if you observe, you will see that if minus 3 times exponential I theta will give me this, minus 3 times minus exponential I theta will give me plus exponential minus I theta. Now, in order to look like this, because we are dealing with sine, 2I must come under each of these. So I can write it like this: minus 1 over 4. 4, 8I means 4 times 2I. I want to bring the 2I inside, so that this one will become exponential I 3 theta minus exponential minus I 3 theta divided by 2I, so that it will look like this: minus 3 into exponential I theta minus this over 2I. So this is 1 over 4 into, this one is just representing sine 3 theta. I told you, whatever value that is here, you only affect the theta. If no value is there, it will just be sine theta. Then minus 3, this is minus 3. The whole one here is just our sine theta in this place. This is sine theta. Now, if you expand, it will just be 3 over 4. Let me bring the minus 1 over 4 times minus 3 sine theta. That will be 3 sine theta over 4. Minus 1 over 1 times it, that will be minus 4 sine 3 theta. So we have proved it. We have proved this. Is what we have to prove, and we have proved it. Another important one is De-Moivres theorem. De-Moivres theorem is an important theorem in complex number. We always use it to expand numbers without using binomial expansion. So that is one of the applications of complex number. And the theorem says that if this z is a complex number in polar form, and if you have a positive integer n, that is, if n is a positive integer, then cos theta plus I sin theta raised to power n is equal to cos n theta plus I sin n theta. What that means is that if you are finding cos theta plus I sin theta raised to power n, then instead of making any silly expansion or stressful expansion, you can just bring down the n to theta and n to theta. That is what the De-Moivres theorem says. So that is, and what we are trying to say here is that let's assume that you're having cos theta, cos 30 plus I sin 30. Let's say we want to expand it raised to power 7. The De-Moivres theorem says don't bother yourself. Just multiply the power and the 30. That is 210 plus I sin. Do the same thing for sin. 210. So we can use it to expand something of this nature. Let's say 1 plus I raised to power 13. We want to expand it. It's very, very easy for us to expand. But this I, before we can apply the Moivre's theorem, it has to be in polar form, but it is not in polar form here. And the proof of the theorem, so you use mathematical induction. Which I have taught you, but you need to go and do that yourself. But anyhow, this is it. You can do it. This is it. This is another proof. This is another proof. Let's now consider the application of this De-Moivres theorem. So it will be another example. Evaluate the following using the De-Moivres theorem. This, and this. So the De-Moivres theorem cannot be applied here, or else we express it in polar form. And thank God I've taught how to express in polar form. Now let's consider this first. Let's say z is equal to 1 minus I root 3. As usual, we know that s is 1, y is minus root 3. I will not stress myself because I have done that before. I have taught you how to do that. Immediately we know, okay, we normally find r first. So we know that without stressing ourselves, r is 2 and our theta is 300. Our theta is 300. So our z is 2 into cos 300 plus I sin 300. Now, we have successfully expressed this in polar form. Then we can now apply the Moivre's theorem. 1 over root 3 raised to power 5. So it's we just raise the whole of this answer to raised to power 5. That will be 2 raised to power 5 into cos 300 plus I sin 300 raised to power 5. So 2 raised to power 5 will give me 32. By De-Moivre's theorem, we don't need to stress ourselves. We only need to multiply this 5 by this. That will be cos 1500 plus I sin 1500. And if we continue, our answer will be equal to 32 into, we can use our calculator to find cos 1500. And when we use our calculator, cos 1500 will give me 2. Sin 1500 will give me 3 over 2. So 2 can still cancel. So what we have left will be 16. 2 cancel 32 is 16. 16 into 1 plus I root 3. So that's our answer. So that means if I had expanded this using binomial expansion or Pascal triangle, my answer would be 1 plus I root 3. So that is the beauty of complex number. Another one is minus 2i raised to power 8. Now, that is the second one. So also, we know that our s is 2, minus 2. Our y is minus 2. I will not need to explain this. I've done all this before. So immediately, we should know that our r is 2 root 2, or simply, what I got is 8. So which can be expressed as 2 root 2. Our theta, I've done that before. Our theta, I don't need this. It's 225 degrees. So in that case, our z equal to 2 root 2 into cos 225 plus I sine 225. If I give you this, you don't need to jump it. You need to tell me how I got all this. Now, what we are looking for is minus 2 I raised to power 8. You only need to put all this to power of 8. 2 root 2, I said is the same. That is 8 raised to power 8 into cos 225 plus I sine 225 raised to power 8. So this one is very easy for us to do. So root 8 raised to power 8 should give me 8 raised to power 4 into, by De-Moivres theorem, we only need to multiply this power by this angle. I'm multiplying it. 225 times 8 will give me 1800. 225 times 8 is also 1800. This is 8 raised to power 4 into cos 1800 from my calculator is 1. Sin 1800 will give me 0. I 0. We don't need this. 0 will vanish it. So our answer is 8 raised to power 4. And 8 raised to power 4 from our calculator will give us 4096. So what we are saying is that if we had expanded this using Pascal triangle, we will get 4096. Oh, this is what we mean by this is one of the applications of the Moivre's theorem. For the third one, go and try that yourself. For the third one, go and try it. Example, another application of De-Moivres theorem. Prove the following by De-Moivres theorem. Prove that cos 2s is equal to this and is equal to this. So we only need, this is how we normally start for this. We only need to know. We say that we know that cos s plus I sine s. We know that all square by De-Moivres theorem will give me cos 2s plus I sine 2x. We know that. So that means cos 2s plus I sine 2s will surely give me cos s plus I sine s all square. Then let us expand this one using Pascal triangle. That should give me cos square s plus cos this times this, that will be I cos s sin s plus another I cos s sin s, and finally this plus I squared sin square s. When we apply the expansion, then we will expand it. Here we have cos square s. Remember, I square is minus 1. So that will become minus sin square s. These two, they are the same thing. So I will add it together. It will be I 2 sine s cos s. So it is this one that gives us all this. So that means I cannot take the real part for real part. This is real part. This is real part. If you compare both sides, you see that cos 2s will now be equal to the real part here, which is cos square s minus sine square s. And you will see that sine 2s will be equal to the imaginary, I sine 2s. We don't need the I. You only pick the value that is there, 2 sine s cos s. So we have shown that cos 2s is this, sine 2s is this, using the De-Moivres theorem. So once again, you can check it. Another one, let's show that cos 3s equal to 4 cos cube s minus 3 cos s, and we show that sine 3s equal to 3 sine s minus 4 sine cube s. All we need to do is that we should know that adding it together with I cos 3s by De-Moivres theorem. Solution by De-Moivres theorem. Let's say this is B. Cos 3s plus I sine 3s will surely give me cos s plus I sine s all cube by De-Moivres theorem. We know by De-Moivres theorem we only need to multiply this and it will give us what is here. Now our aim is now to expand the other part. So let's use Pascal triangle. So this will give me cos cube s plus 3 cos square s into I sine s. The next one will be 3 cos s into I sine s all squared. And the last one is I sine s all cube. Now we need to expand from this place. So this will give me, this will be equal to cos cube s. This is, let's bring the I out, plus I 3 cos square s sine x. That is for this one. I 3 cos square s sine s. But for this one, I square, this this one will give me I square sine square s. But I square here is minus 1. So our answer will just be minus 3 cos s sine square s. So what we are going to have there is minus 3 cos s sine square s. Finally, for this one, it will give me I cube sine cube s. But I cube is same thing as minus I. So what we just have there is minus I sine cube s. So let's write out the real part. So what we have done is that cos 3 plus I sine 3s will be equal to, we bring the real part together, cos 3s and this minus 3 cos s sine square s plus the imaginary. So the I 3 cos square s sine s minus sine cube s minus this one. From that side, we can now compare. Our comparison will yield 3s. We compare the real part to real part, will be cos cube s minus 3 cos s sine square s. Also, sine 3s is equal to 3 cos square s sine s minus sine cube s. So that is that about that. But if you can see here that it has not gotten to where we are going to, because where we are going to is 4 cos cube s minus 4 minus 3 cos s. This is not it, but it's very easy for us. Let us just recall this. Recall that sine square s is 1 minus cos square s. Also recall that cos square s is vice versa, is 1 minus sine square s. This cos 3s will now become cos cube s minus 3 cos s. So instead of this sine square s, I can write it as 1 minus cos square s. That will be cos cube s minus, if you expand, we have minus 3 cos s. Minus 3 times this, that will be 3 cos cube x. If you add it together, this is cos cube, this is another cos cube, it will become 4 cos cube s minus 3 cos s. So we have proved it. That is it. Yeah. But for this one, you go and do it yourself. The second one, you only need to turn this cos square s to 1 minus sine square s. When you have done so, you are going to get the required question. Another important concept of complex number is roots of complex number. That is how to find, let's say, square root, cube root, and all those things inside complex number. And this root is an extension of De-Moivres theorem, because De-Moivres theorem deals with power. And we know that if you have a power in fractional form or in a rational form, we have, that is what we call a root. For instance, we know that square root of s simply means s raised to power half. This is power of fraction, which is root. So we can apply complex, we can find the root of complex number too with the application of De-Moivres theorem. And that says if z is equal to this, then z raised to power 1 over n, which is root of z, nth root of z, is r raised to power 1 over n cos theta plus 360k over n plus I sin theta plus 360k over n, where k is 0, 1, 2 up to n minus 1. Now let's take example. Let's evaluate this. We want to evaluate cube root of 27. Remember that normally cube root of 27 is 3. This is one of the advantage of complex number over real number. If it is real number will just tell you that the answer is 3. But complex number will say that since it's cube root, we must have at least we must have 3 values, that if you cube it, it will give you 27. Now let's get to action. Now let's consider the 27. Everything depends on expressing it in polar form. In this place, my s is 27, my y is 0. There's no y there. Y is the imaginary. There's no imaginary. So in that case, our r will be root of s squared plus y squared. I don't need to do that, but let me just give you, it's 27. While our theta is arctan x, arctan y over s, that is arctan 0 over 27. So arctan 0 will give me 0. So our theta is 0. So those are the two things we need, our r and our theta. I will now come here. Therefore, cube root of 27 will be equal to, use the formula, our r. This is 27 raised to power 1 over 3 raised to power 1 over n. You know, our n is 3. So let me put it there. N is 3 because we are looking for cube root. Into cos, what we have there is theta plus 360k. Our theta is 0 plus 360k over n over 3 into the same thing we go for sine. 0 plus 360k over 3. And cube root 27 raised to power 1 over 3 is just 3 by indices. What we have left is cos 360 divided by 3. That is 120k plus I sin 120k. So that is what we are going to have. Now we will now start by to look for the values of all this using the values of k here. We have said that here that k is 0 to n minus 1 means 0, our n is 3, then k will move from 0, 1 to 2 to n minus 1, that is to a number right before the n. Our n is 3, so we can see 1, 2, 3, but it will start from 0. K value will run from 0, 1, 2. From this place, you start from when k is 0. When k is 0, the first answer z1 will become 3 into cos 0 plus I sin 0. That is just 3 because cos 0 is 1. Okay, let me say 3 into 1 plus 0. That is 3. So that means cube root of 27 is 3. The next one, we find the value for k is 1. For k is 1, our z2 will be 3 into cos, that will be 120 times 1 plus I sin 120. This is 3 into, when we find it from our calculator, cos 120 will give me minus half, then plus I sin 120 will just give me root 3 over 2. So we can bring the 3 out, that will be the 2 out, that will be 3 over 2 into minus 1 plus I root 3. So it's our answer. So this is another cube root of 27, because if you find the cube of this, it will give you 27. Finally, when k is 2, so the third one will now become, when k is 2, you are going to have, just put k to be 2 here, 3 into cos 120 times 2, that will be 240 plus I sin 240. But from our calculator, cos 240 will give me minus half plus I sin 240. Sin 240 will give me minus root 3 over 2. So I can bring the minus out. Minus is common and 2 is common. I can bring the minus out so that we are going to have minus 3 over 2, 1 plus I root 3. So that is the value. So these are the values of cube root of 27. This, and this will give us cube root of 27. Let's consider another example. To evaluate cube root of 3 minus I root 3. From this place, our x is 3 and our y is minus root 3. The I is not there. So without stressing myself, which I have taught you before, I will not stress myself there. My R is 2 root 3. While my theta, if you do it very well, you are going to get 330 degrees. But our formula, the formula we are using is this. Now, we substitute the value. Our n is 3 because we are still looking for cube root. So z raised to power 1 over 3 will now be 2 root 3 raised to power 1 over 3 into cos our theta. Theta has been 30 degree, 330 plus 360k over n. Our n is 3 plus I sin the same thing, theta 330 plus 360k over 3, which can be written as 2 root 3 raised to power 1 over 3 into cos. This one will give me 110 plus 120k, because 3 cancel this, plus I sin the same thing, 1110 plus 120k. So what's our k? K has to be in 3 because n is 3. So k will be 0, 1, we stop at 2. If n is 5, then k will stop at 4. Now, for k is 0, our z1 will just be 2 root 3 raised to power 1 over 3 into, when n is 0, what we are going to have is cos 110 plus I sine 110. So we get this from our calculator. We get cos 110 and sine 110 from our calculator. That is an answer. When k is 1, so the second one will be, we'll just be using this deduction to get our answer. So when k is 1 now, that is cos 110 plus 120 plus I sine 110 plus 120. So this is 2 root 3 over 1 over 3. So this is 110 plus 120. That should be cos 330. Cos 230 plus I sine 230. So we find this from our calculator to finish it. And finally, when k is 2, z3 will be 2 root 3 raised to power 1 over 3 into, so this is what we are using, cos 110 plus 120k. K is 2 now. That is 120 times 2.